Hello everyone, welcome to this promo video of our KDD paper. This work is driven by a real study where we want to develop a predictive yet explainable model to capture the interactions between the organ failures and dysfunctions that precede sepsis. We take the linear multivariate Hox process model and we apply rate-limiting function on the conditional intensity to ensure its positivity in the presence of inhibiting effects. Typical estimation method maximizes the log likelihood. However, the evaluation of the true likelihood requires calculation of the so-called restart times. Whenever there is one event occurring that inhibits the subsequent event, it's possible that the linear combination in the intensity becomes negative and it will take some time to restart the whole process. Unfortunately, the restart time calculation is computationally intense. To make things even worse, the empirical optimizer lies on the border of the feasible region and it poses challenge to the tempting gradient-based method. As verified by the fourth column, gradient descent with log likelihood as stopping criterion typically fail to recover the interactions among the events. To fix this issue, we propose a surrogate likelihood formulation, which is the log likelihood for the intensity without the rate-limiting function. As an approximation to the true likelihood, it is computationally efficient since it does not require calculation of the restart times. Moreover, it is easily differentiable and the gradient is well defined even outside the feasible region, suggesting that we can use a matrix for business norm as the stopping criterion for gradient descent. However, as shown in the third column, naively using the gradient norm stopping criterion will lead to unsatisfying performance. To fix this issue, we propose a two-phase training procedure. In the first phase, we restrict our consideration to triggering effects only by projecting negative magnitudes back to zeros. Subsequently, for those magnitudes whose ground truth values are negative, the convergence is not attained, which is characterized by the large gradient norms, and before the second phase gradient descent to correct this bias. As we can see, even though the log likelihood no longer exists in the second phase, the estimation error continues to drop as the gradient norm decreases. Thank you.